Skill 1. Woo! It's exciting. Now, we're going to be talking about a lot of identities this unit, and you guys actually know some already. We didn't call them identities because at the time they didn't need that label. Okay, but now that we're throwing in more identities, you do need to understand that you already know some. For example, cotangent. Cotangent is the reciprocal of tangent. So we can rewrite it as such. That's a reciprocal identity. You can also write cotangent as the cosine of theta over the sine of theta. That's a basic trig identity. The secant of theta is another reciprocal identity that can be written as 1 over cosine of theta. That doesn't look like a theta. There we go. We know that cosecant of theta can be written as 1 over sine theta. Again, another reciprocal identity. We also know that tangent can be written as sine of theta over cosine of theta. A basic trig identity. But we can also write it as 1 over cotangent of theta. We don't see this too often, but it's an option. So it's good to have it down. Okay, here are some of your basic identities that we already know, but now we can classify them as such. Think about if I were to ask you to simplify 2 fractions, right? Well, really, one's an integer, but we can change it. We can change it to be x over x. If I need to combine 2 terms, one of them is a fraction, I want to get common denominators, and so I did. We know this is an option mathematically. We also know that if the numerator doesn't have any like terms, we can write it as x plus 3 all over x to combine the 2 fractions, even though the numerator doesn't have like terms. This is a possibility. Okay, well, what if I ask you to combine sine squared of theta plus cosine squared of theta? Yikes. Okay, hang on one second. Well, we can rewrite this as the sine of theta squared plus the cosine of theta squared. But that doesn't really help us. There aren't any denominators to combine. They're different trig functions. I'm going to put a big fat question mark. Yeah, question, Natasha?
Okay, so on the last one, why couldn't you cancel off the x's?
Ooh, good question. Okay, so canceling out the x's when we're here.
Yeah.
Okay, because the numerator is its own quantity. So if I take from one part of the sum, I have to take from both. Yeah, so good question. Be careful of that. Okay. Well, sine squared plus cosine squared, is actually going to lead us to our Pythagorean identities, ladies and gentlemen. I would like to introduce you to the first Pythagorean identity. And it says this: sine squared of theta plus cosine squared of theta is equal to 1. So we can simplify it after all. What in the heck? Where does this come from? Well, think about our unit circle, right? We use the unit circle because it was the most simplified form of all of our trig ratios. And we had this triangle with the reference angle at the origin. And we found out, well, okay, so if I travel x units this way and y units this way, I have a point x comma y. And then we found out that, oh, even cooler, this correlated to the cosine comma sine. And since it's a right triangle, the Pythagorean theorem applies. So we could say that x squared plus y squared, and since it's the unit circle, the hypotenuse was 1. And then, going back to what we found out, this means that the cosine squared of the angle plus the sine squared of the angle is equal to 1. Our Pythagorean identity number 1. Now there are variations for all of our Pythagorean identities, so I'm going to list them below. Just by using basic arithmetic, I can subtract sine squared to both sides. Why not? So that would leave us with the cosine squared of theta equal to 1 minus sine squared theta. Just a variation of the first. Well, we can also subtract cosine squared theta, leaving us with the sine squared theta equal to 1 minus cosine squared theta. Okay, so there's our first main Pythagorean identity with the variations following behind it. Well, subtraction's so mainstream. Let's get exciting, yeah? If we have sine squared theta, maybe, there we go, plus cosine squared theta is equal to 1. Let's divide. Yeah, let's divide every term by sine squared theta. And we're allowed to do this because we're not changing the equation. We're dividing every term by the same value. Well, what is sine squared theta divided by sine squared theta? Aiden?
1.
Yeah, good. It's just 1. What is cosine squared theta divided by sine squared theta? It's okay. It's okay. Yes! Good. It's cotangent squared theta. And then what's 1 over sine squared theta? Aiden? Cosecant squared theta. I present to you the second Pythagorean identity. We have 1 plus cotangent squared theta equal to cosecant squared theta. And of course there's variations to this as well, because we can subtract the terms from one side to the other. So if we subtract 1 to both sides, we end up with cotangent squared theta equal to cosecant squared theta minus 1. If we subtract cotangent squared theta to both sides, we end up with 1 equal to cosecant squared theta minus cotangent squared theta. Okay, well, we can't really leave out any trig functions because their feelings will get hurt. So if we have sine squared theta plus cosine squared theta equal to 1, okay, that original Pythagorean identity. We already divided through by sine squared, so let's divide through by cosine squared. And let's see what we get. Well, what is sine squared theta divided by cosine squared theta? Yeah. Beautiful, yep. Tangent squared theta, thank you so much. And what is cosine squared theta divided by cosine squared theta, Jada? 1. And last but not least, 1 divided by cosine squared theta. Yes, good. Secant squared theta. Nice work, everyone. Enter in our third Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. And of course, we do have variations as well. So let's subtract tangent squared theta to both sides. We end up with 1 is equal to secant squared theta minus tangent squared theta. And if we subtract 1, we end up with tangent squared theta is equal to secant squared theta minus 1. I've always found these to be really fascinating because it's all derived from that original sine squared plus cosine squared. Now, if you are planning on memorizing these rather than having to rely on your notes as you're trying to get through these proofs, my suggestion is always to focus on the top 3. Obviously, everything stems from sine squared theta plus cosine squared theta equals 1. But if you can memorize these top 3, the rest of the variations, the other 6, you can easily write down as you need them. All right? Now, why do we need them? Because we're going to do proofs. Woo! Here we go. Yeah, thank you. Thank you. Peyton, stop shaking your head. No. Example number 1. Now, a couple things to remember. If you're asked to show or verify, you cannot manipulate both sides at the same time. Okay, that is super important, and we're going to forget that from time to time. So I'm going to say it one more time in the hopes that you write it down so you don't forget. When you're asked to show or verify, you cannot manipulate both sides of the equal sign at the same time. Okay, you're going to pick one and you're going to work with it. If you have to start over, that's fine, but you can't use them both at the same time. So if I've just shattered your dreams, I don't feel bad. Those are the rules. Okay. Just kidding. I do feel bad, partially. All right, so we're going to pick one, and we're going to work with that. Now, the second thing that you need to be aware of, for example number 1, it's asking us to show that 1 plus cotangent squared theta equals cosecant squared theta. Unfortunately, you cannot just write, oh, it's true because it's a Pythagorean identity.
That would be nice.
I know, it would be nice. However, trig is not nice. I'm just kidding. It's not the point, right? Our point is to prove it. Prove that it actually is an identity. So I can use other identities to prove it. I can't use itself to prove itself. Hopefully that makes sense. Let's delve into it. Well, I hope. I don't know. We get to pick a side and try to make it look like the other side. I have a binomial that equals a monomial. I'm going to choose to start with the left-hand side because I have more to work with. And it's going to be a little bit easier to combine 2 terms into 1 rather than split 1 term into 2. Okay? So I'm going to, let's rewrite. We can rewrite cotangent. So I'm going to, oh, no, I'm not. I'm going to rewrite cotangent into its form of cosine squared theta over sine squared theta. Okay, I'm choosing to work with the left side. I rewrote cosine squared theta over sine squared theta. And I did this in the hopes of trying to combine the 2 terms. Well, here I see that I could get common denominators. So I'm going to write 1 as sine squared theta over sine squared theta plus cosine squared theta over sine squared theta. I changed 1 to have common denominators in the hopes that I could combine the 2 terms, and we can. So let's rewrite the numerator as sine squared theta plus cosine squared theta all over sine squared theta. Keep in mind your end game. Where are you trying to go? Where are you trying to get to? For this particular example, we're trying to get 2 terms into 1, particularly cosecant squared theta. Well, that numerator looks familiar. Can I substitute something into the numerator for sine squared theta plus cosine squared theta? One, yes. We can substitute, nice job. We can substitute 1 in for the numerator. Now, something I didn't mention but you need to be aware of. Notice your Pythagorean identities are all squares. So sine squared theta plus cosine squared theta equals 1. sine theta plus cosine theta does not equal 1. Okay, the Pythagoreans have to be squared in order for them to actually exist. All right. Oh, do you see what I see? We can rewrite 1 over sine squared theta using the reciprocal identity to be cosine squared theta equal to cosine squared theta. We have shown that one side equals the other. Right? That's exciting. I told you. We're just starting out. Jada.
It made sense until like the last step. What did you do to make it equal each other?
Oh, okay. So we know that 1 over sine squared theta, where is it? Right here, can be rewritten because it's the reciprocal. So I just rewrote it using that identity.
Okay.
Thanks for asking. Also notice, please, I didn't skip any steps. It is so vital that as you write out your proofs, hang in there, Erin, as you write out your proofs, do not skip steps. You will lose points for an incomplete proof if you skip steps. Okay? For example, I wouldn't want to write 1 over sine squared theta equals cosecant squared theta because they don't equal each other. 1 over sine squared theta can be rewritten using the reciprocal identity, and then they equal each other. Okay, so please make sure you're very thorough. All right, example 2. Ooh, hello. Verify. That means we can only work with one side at a time. Okay, well, for A, we have the sine of theta times the cotangent of theta, and it equals the cosine of theta. The left side, again, has more to work with than the right side, so let's work with that side first. See where it takes us. Sine of theta, that's pretty straightforward. Cotangent of theta, since we're trying to get our terms to be cosine, well, bless you, let's rewrite cotangent into sine and cosine. We'll leave sine theta as is, but I'm going to rewrite cotangent to be the cosine of theta over the sine of theta. Again, I rewrote it because I'm trying to end up with just cosine of theta, so I want to make sure everything's in similar terms. All right. At this point, sine of theta is over 1. We don't ever write it because it's the 1, right? We don't need it. However, we could cancel. So if sine of theta is in the numerator and sine of theta is in the denominator, they can cancel out. And we are left with cosine of theta, which is exactly what we needed. And we're done. Yeah, Natasha?
So we could cancel those out because they were solid identities because it was a multiplying thing, right?
It's the same as if I had x over 1 times 3 over x.
Yeah.
Yeah, totally.
Yeah.
Does that answer your question?
Yeah.
Okay.
I just wanted to verify.
Oh, no, absolutely. Thanks for asking. Peyton?
What happened to the square? On the last one, how
Yes, you can't use the Pythagorean identities if the terms are not squared. So it's only for the Pythagorean identities. Yeah, thanks. 1 over sine squared theta. Okay, hang on one sec, Jada. Artie, and I don't understand because they aren't equal. What number are you looking at? All right, here we go. Example 2b. To be or not to be? I never get tired of that joke. Here we go. 1 minus cosine squared theta over sine theta is equal to sine theta. Again, the left-hand side has way more options than the right. So let's work with the left-hand side. Any ideas? 1 minus cosine squared theta. Aiden?
Sine squared theta.
Very good. And where'd you get that from?
The Pythagorean identity.
Say that 5 times fast, right? Yes, excellent. The Pythagorean identity, that first one of the variations is 1 minus cosine squared theta. So we can substitute sine squared theta into the numerator. And remember, if you have sine squared theta, okay, the squared is always written right after the sine in between the angle, that's equivalent to sine theta quantity squared. So if I have sine squared in the numerator and sine in the denominator, I'm going to reduce by 1. You can think of it as, if you need the visual, sine of theta times sine theta over sine theta. Okay, now you don't have to write that step. It's just for those that need to see it pulled out. So we can reduce one of the signs, leaving us with sine theta equal to sine theta. Yeah, this is the optional step. It's just for people that need to see where it came from.
You just said we have to write out all the steps.
I did, yes, but I'm glad that you clarified. I just said no, you don't. That one's optional. Yes, thank you. Thank you, thank you. All right, example C. Ooh, yay, more to work with. Woohoo! Okay. Sine squared theta times secant of theta plus cosine of theta is equal to secant of theta. Well, yes, again, I am going to choose to work with the left side. It's just happenstance that we're working with the left side, okay? You can work with the right. And my goal is to get secant of theta, which I'm thinking is 1 over cosine in its reciprocal form. So let's change secant and see where that leads us, all right? So I'm going to keep sine squared theta as is for right now. And then I'm going to change secant to be 1 over cosine theta. My surface is lagging right now, I'm really sorry. And then we have plus cosine theta.
Better than yesterday when the internet went out.
The internet went out? God
Every
bless.
single period.
Okay, on that left term, let's multiply across. So we end up with sine squared theta over cosine theta plus cosine theta. Well, I still have 2 terms, and I'm trying to get them to be 1. So on that right term, I'm going to put a 1 underneath. Let's get common denominators. So I'm going to multiply that second term by cosine theta over cosine theta so that I can get common denominators, which leaves us with cosine squared theta over cosine theta. Now that we have common denominators, let's combine that numerator to be sine squared theta plus cosine squared theta all over cosine of theta. Man, sine squared theta plus cosine squared theta, what is that? Just 1. Yeah, it's our Pythagorean identity. It's that main one. So I'm going to substitute 1 into the numerator, since that is our Pythagorean identity, leaving us with 1 over cosine of theta. And then, Connor, I see you seeing it, that is our reciprocal identity. I'm going to change 1 over cosine theta to be secant theta is equal to secant of theta. Woohoo! Trig proofs. Party time. I've got one more for you. If you go to the, oh, no, just kidding. I always forget about example number 3. Well, no. Let's jump to the you try real quick. Number 3. And then we'll go back to example number 3. Okay, so under the you try for number 3, back in fall semester, okay, I'm pretty sure most of you have forgotten about fall semester. But back in fall semester, we were dealing with complex numbers. We were dealing with the imaginary unit. And we came across this term that I was so excited about called the conjugate. Don't forget about the conjugate. The conjugate has not gone away. The conjugate is 2 binomials with the same terms but the opposite operation. And I was so excited because you don't have to FOIL. This is where I gave you the freedom to cut out the oi. And many of you laughed at me, but the joke's on you because it made everything easier, right? We only had to multiply the first and the last. Why? Because we ended up with the middle terms being identical. Okay, the conjugate was a beautiful thing. So those middle terms canceled out and you were simply left with the first and the last. This helped us with our complex values because it got rid of the imaginary unit in the denominator. You're going to see conjugates used a lot in proofs. Enter in number 3. I cannot simply change the denominator to be sine of x on the left-hand fraction. Okay, it's not squared. Now, if it was 1 minus cosine squared of x, we could easily change it, but it's not. However, I could make it to be what I want. In other words, if I multiply the numerator and the denominator by the conjugate of the denominator, I automatically make my denominator squared, ultimately opening the door for me to use my Pythagorean identities. Okay, this is just one way to approach it. It's not the only way. In multiplying the top and the bottom by the conjugate of the denominator, I'm not going to distribute the numerator. You can, but ultimately my goal is to get 1 plus cosine of x. Multiplying sine squared into this binomial is not going to help me get there, so I'm just going to leave it outside. Now, in the denominator, since they're conjugates, I'm only going to multiply the first term and the last term, leaving me with 1 minus cosine squared of x. Is this one of our Pythagorean identities?
Yes.
It is. What does it equal, Natasha?
Sine squared x.
Perfect. So at this point, since we've made the denominator a squared term, we can simplify and substitute in sine squared of x in the denominator because it is one of our Pythagorean identities. And then it cancels out. Perfect. We have a sine squared x in the numerator, a sine squared x in the denominator. They reduce. We're left with 1 plus cosine of x, which is exactly where we need it to be. Okay, so when we're working out proofs, when we're verifying, when we're showing, you can only manipulate one side. You can't go back and forth. All right? Now, it might ask you to simplify. Travel back in time with me, please, to example number 3. Come on, Surface Pro. There we go. Notice it's an expression. It's not an equation. We are not verifying. Numbers 1 and 2 on the you try are expressions. You're not verifying. You're simplifying. When it asks you to simplify, your goal is to get rid of fractions, to combine terms, to use identities, to simplify as far as you can go. Okay? Excuse me. I wouldn't want to leave it as sine squared plus cosine squared because that can simplify to 1. All right? You need to simplify as far as you can go. All right. Looking at this, I see lots of squares. Could we substitute something into the numerator from our Pythagorean identities? What?
Oh, no.
Yeah, Aiden? Good. Cosecant squared. And the only reason I asked that is because I saw that they were squared terms. Okay, so I'm automatically thinking Pythagorean. So let's substitute cosecant squared theta into the numerator, since that is the Pythagorean identity. And then fractions are division, so I'm going to write this out horizontally as a visual reminder that that's the operation that's happening here. And then I'm going to use the reciprocal and the basic identity to rewrite both trig values. I'm going to change cosecant squared theta to be 1 over sine squared theta divided by, and let's change cotangent squared theta to be cosine squared theta over sine squared theta. This is kind of nice that they're in fraction form because now we know, well, shoot, I'm dividing fractions. So let's keep the first. So we'll keep 1 over sine squared theta as is. Change the operation to multiplication, and then apply the reciprocal of that second fraction. Now we can, yes, simplify the sine squareds, cancel them out. And we're left with 1 over cosine squared theta when we multiply across. But this is not simplified because 1 over cosine squared theta is an identity, right? It's the reciprocal identity. So in simplified form, it would be secant squared theta. Right? And that's our final answer.